Optimize. A journey through database query optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
Today, now we're continuing on, like I said, we're going back and forth between bottoms up and top down and looking at the sort of core aspects of the search implementation or the algorithm implementation. So today will be a discussion on how to parallelize the search in for a bottoms up, and then on Monday's class, excuse me, next week, that'll be looking at how to apply it for the top down approach, which we've already started seeing inklings of that in the last class when we talked about how the pruning method, whether it was accumulated or predicted, you know, the accumulated one required you to sort of go down and do something, and that sort of blocked other threads from exploring other parts of the tree. The bottom up isn't going to have that problem, but we'll address that again, that issue again next Monday for top down. All right, so as I said on Piazza, okay, I had no office hours today. Send me an email if you want to meet, and then I'll follow the people who already have emailed me. Probably be like for tomorrow. I may be on campus tomorrow, depending what the flu test says. Project 1, again, is due Friday, February 28th. For Project 2 topics, for next class, we'll start going over some potential directions you may want to pursue. Again, you don't have to decide right away, not until I think before after spring break. And then after spring break, what you want your Project 2 to be based on. But at least you can start talking amongst yourselves to figure out what groups you want to you want to form. And then we'll post on the spreadsheet what groups you want to be in. And if you're not in a group, we'll have like a sort of side buffer that you can put yourself in as a free agent. And then we'll figure out how to assign you to a group afterwards. And again, for Project 2, it's open-ended. It's supposed to be, you know, ideally touch on the things we've talked about in this class. But there's other areas about, you know, database optimization, query optimization that you're curious about that you're doing in your own research for, you know, some other class or something else. I'm all for combining ideas, right? So don't assume, just don't think, oh, whatever I talk about next week, those are the only ones you can pick, right? If you have a good idea, then I'm all ears. Okay. All right. Any questions about Project 1? Okay. All right. So, all right. Last class, we, as I said, we started looking at we were looking at how to do the top-down joint enumeration, and one of the techniques that we saw was this idea of partitioning the query graph into subgraphs or smaller connected graphs, and that was done in such a way to not necessarily paralyze the search, but at least be more targeted in how we're doing the search going down. But it doesn't take much to stretch the imagination to say, well, if I'm already partitioning the graph, you know, if those partitions or the subgraphs are independent, I could start exploring them in parallel across different threads. So even though last class we saw a partitioning technique, and that was the idea of sort of narrowing down on the parts of the graph you think are going to be providing those benefits, so try to optimize those first before you run out of time. We'll see basically the same technique today in next class of how doing the same thing to paralyze things. And as I said, the challenge is going to be is that there's going to be dependencies between different parts of the solution space within the join graph that we're trying to enumerate upon, where we're going to have to do some part first before we can start exploring other parts of the tree, right? Meaning like we have to know the answer for some things, for some part of the join graph before we can start saying, okay, let's look further down the tree and start looking at those other stuff. For again, we saw this in accumulated cost versus predicted cost bounding. In top down, this is more of an issue because if you're doing accumulated cost, you need a physical cost. You need a physical plan to at least get that first initial cost to figure out what your upper bound is going to be. So you kind of need to have one thread go down to at least the bottom, generate some physical plan, even though it's not ideal. Just have something, and then once you have that, that can then unlock a bunch of other stuff. But we saw this in other cases too, where we talked about doing transformations from an outer join to an inner join. Well, you can't start doing join enumeration on the inner join until you apply the outer join transformation, right? So like that's another example where like you have to do certain things before you're allowed to get a more I don't say exhaustive, but a wider search into the different options you could have for a query plan. So as I showed this before, like what we're trying to figure out now is we know the general framework of how to design a query optimizer, and whether it's top-down or bottom-up. And now we're trying to say, okay, what can we do to ensure that our query optimizer actually produces good query plans for whatever SQL query shows up? And so we're at this point here where we're trying to understand how to make the search algorithm as efficient as possible, and obviously accurate as well. But you'll see in all the algorithms we'll talk about today, there's always these explicit checks to see if I try to partition the graph in a certain way, is that going to make me disconnected? Therefore, that's going to introduce either correctness issues or Cartesian products, which is an efficiency issue. Like, there's a bunch of checks we have to do to make sure that we're producing accurate and correct results. But now we're kind of also really focused on how can we make this run as fast as possible. So that's what this class is, and then for next week, and then we'll start talking about the cost model, which is kind of this big albatross that's hanging on the side that we haven't really addressed, right? All right, so up until now, also too, say for all the methods we've talked about, with either the implementation of the framework or the algorithms to do join enumeration, they've all been assumed that you're running in a single-threaded environment, right? And so the goal, again, what this class and next class is about is how can we make the query optimizer run the search in parallel. And the challenge here is that most query optimizers are not going to be parallel, right? Even for most modern systems, they're not going to be parallel, right? So the optimizer itself is going to be a single-threaded component of which the database system will allow multiple threads to run at the same time. So it could be optimizing multiple queries or independent queries at the same time, but they don't take, for one single query, spawn a bunch of worker threads to then do that search at the same time, right? And this is for two reasons, right? One is for historical reasons, because most database systems up until really Snowflake made it big in 2013, or that sort of architecture came along. Like, most database systems were these single node monolithic architectures where everything you needed to do to run your data system was on a single box or within a single program, if you will. I don't want to say process because it could be a multi-process system, but like it's assuming you're running everything on a single box. That means when a query shows up, it goes through this connection handler thing, and then that goes to the parser, then the binder, and then it goes to the optimizer, and all that's running on the same machine where you're actually running queries, right? Like, this is what MySQL does, what Postgres does, SQLite, Oracle, SQL Server, right? This is how people built these systems since the 70s. And so the challenge is going to be now, if I want to have a parallel query optimizer, well, now I'm taking threads away, workers away from other parts of the system just to do query planning, right? And so again, if I'm running on a single box, I'm not elastic. I can't just magically conjure up more threads. They got to come from somewhere. So I'm taking away threads that I could be using for background tasks or query execution, and they're using them for query planning. So that's a hard thing to do in terms of like, how much better does my query plan actually be if I'm multi-threaded versus just throwing more hardware at the problem. Again, the multi-core stuff, that's really only early 2000s. From the 80s to the 90s, most machines were like a single CPU with a single thread. The enterprise stuff was a little bit different, but like most of the time you didn't have all the threads that we have, or cores we have today. All right, so that's a historical reason for monolithic database system architectures. But even now, also in a cloud environment, something like Snowflake, they're still going to have a single-threaded query optimizer, even though it's running as a service. So again, multiple queries can get optimized at the same time. Again, within the context of a single query, that's going to be running as as a sort of single-threaded context. So the goal for doing parallelization is that even though the search problem is NP hard exponential, we want to have the search time to trying to find optimal plans. It should improve linearly in regard to the number of cores we're given it. So if I go from 1 core to 2 core, then my time should be, in theory, cut in half, right? Again, as we talked about before, it depends on what the stopping mechanism is for the optimizer, right? If it's a wall clock time, then you have to then account for that in your implementation or in your setup. So even though you add more cores, you have a parallel optimizer. If you set it to run for 20 seconds, it'll still run for 20 seconds, right? Maybe it exhaustively finds, maybe it gets through all the possible choices and it just quits. but you'd have to account for that. But again, if you do like the Microsoft way, where you say how many transformations you're allowed to do, then now that you would automatically scale that time out as well as you add more cores, because things are just running faster. All right, so the challenge is going to be why this is going to be hard to do. Unlike other parts of a database system, right? Again, we think of like parallel execution of a database system. We know how to do that really, really well. We know how to do parallel scans. We know how to do parallel joins, parallel sorting. Right? All those tricks we've been doing since, really since the 80s, right? But this is a bit harder to do now. It is somewhat similar to query planning or parallel query execution, right? Where you have these pipeline breakers. You kind of need to wait to finish some pipeline before you let another pipeline start running, because it depends on the output of this. So that's sort of the challenge that we're trying to face here. It's that sort of dependency. And so for join enumeration, this sort of the class of algorithms that we've been looking at for dynamic programming are called non-serial polyadic. And so non-serial just means that the computation that we're going to do at one phase or one level, like think of like the search tree, well, it's going to depend on multiple levels of results from the search tree below me. A lot of times in dynamic programming, it's just like, all I care about what the last one was, the last level. But in this world, we care about everything since the beginning of the query, right? Because in order for me to know how I want to join things maybe up above, I'm relying on some computation I did at a lower part of the tree, assuming I'm going bottom up, to figure out the optimal join ordering for some tables down below, right? And then the polyadic just means that, think of like the recursive call we're making for our search. We're passing in two parameters. Like we'll see this in like some of the algorithms here. Like you got to know what the left side of the tree and the right side of the tree are, right? And that complicates what you're allowed to, how you're allowed to parallelize things. So it's a more restrained environment. It's just like, it's not, we're magically going to throw more cores at a problem, and it's all going to, just get magically faster. There is some intelligence we have to put in our decisions of how we're going to split things up. So the basic idea of how we're going to do this, though, at a high level, is going to be the same thing we do when we want to parallelize query execution, right? We're going to partition the search space in such a way that we can divide the work evenly among the tasks of the work evenly among the workers, so that at any time during execution, every worker always has something to do. There's not like a bunch of threads sitting idle polling for work, right? That's hard to always achieve, but in general, we should be okay with this. And then the other challenge is going to be, or the other technique we're going to use is, well, once we split things up into partitions, it'd be really nice if that we could then have other tasks be able to execute without being dependent on what other workers are actually doing. So the idea is that you want to sort of localize, almost like a pipeline, a bunch of work we want to do in our search, so that one worker can kind of do a bunch of things and just rip through the computation without waiting for other workers to produce some result. All right, this should not be, if you're taking 418 or 618, right, all of this should not be new. And we discussed this in 721 last year. All right, so I'm going to briefly talk about three algorithms today. The one would be sort of the straw man that came in the paper you guys read about this dynamic programming for subsets, which is basically the same thing as System R, but with slight difference of what the method in which they're going about and generating the subsets. And then we'll talk about the massively parallel DP algorithm from the paper you guys read. The paper's okay. What I like about it is that it covers like sort of the background of like, here's what an algorithm is based upon. I also like it because it's one of the only ones that, actually, it is the only one that I know of that runs on a GPU. But there's another paper from other people that runs a GPU that predates this one, but this one covered everything. And also they're doing that additivity piece, or that technique from the hyper guys as well. So there's a lot of ideas sort of thrown into one, which I like. The writing's okay. Well, we take that offline. All right, then I'm going to finish up talking about another approach to do called multi-plan join DP. And this is from one of the guys at IBM, but it was done by IBM Research, but this was not part of Starburst or DB2. It was a sort of side project. All right, so the the DP sub algorithm is going to serve as the basis for what the MPDP algorithm is, or MPDP algorithm is going to do. And the basic idea, again, as I said, this is just going to be more or less the same thing as system R, except how they're going to construct the subsets and do that exploration is going to be slightly different. And the basic idea is that we are going to split the join graph based on vertices into subset sizes based on the number of vertices, and that's going to slowly get bigger and bigger, meaning we'll start looking at more larger and larger subsets. And then for each of the different subsets we have, we're allowed to split them up as long as there is a way to connect sort of the left side and the right side, the two subsets that we're looking at. And then we just do do the standard stuff of like, okay, what's the best way to evaluate the join on these two subsets? Is it better than the best plan we've seen so far? If yes, then it becomes the new best plan. Otherwise, we throw it away, right? And again, just like before, we have to do a bunch of steps to make sure that if we split up, we start splitting the query graph into subgraphs to avoid Cartesian products, we got to make sure that we don't have any disconnected nodes. So again, I don't normally like to show code, but I just want to visualize what's going on here. Again, the algorithm is pretty basic. Right, you start at the beginning here, you say, okay, I'm going to start looking at subsets, these are starting of size 2. Right, so you just generate all possible enumerations for all possible subsets. And again, in this one here, when they generate the subsets, they're not actually checking to see whether they're connected or not. They're going to do that later. Right? Remember we talked about how in the case of the hypergraph one, where they would make sure that they only generated subsets that were valid rather than checking after they've generated them to see whether they were valid or not. This one just generates all of them. All right, so then we get down here, and now we're going to go through all the different subsets, again, starting with size 2. And for this one, again, you just start picking each one, and you take whatever is on the left side here. And then this part of the loop here can now be done in parallel. So within one sort of subset, in this case here, it's only size 2, right? But for each of these, I could have a different thread now evaluate the best join order for that part of the subset in parallel, and they don't need to coordinate with each other because there's no information I need to know about what's the best join plan for sort of the subset that I'm looking at. There's nothing I need to know about your subset, right? So again, they're just going to do that system R approach where you just go through and expand out. So this one here, do I look at a hash join or a merge join? Then same thing, I keep fanning out, right? And relying on what came down, down below me to tell me the path I'm going to generate. And I'm not showing this because it's PowerPoint, but like you can think of all possible combinations for the subset size 2 and all the possible combinations of additional subsets. Like this keeps going over and over again. But again, here, the important part here is like this is where they're going to check to see whether if they split a subgraph off of the sort of the main graph they're looking at, is it going to be disconnected? If yes, then they discard it. If no, they're allowed to proceed and do it. Right? And this is just the system R stuff that we said before, but it's slightly composed differently. Yes?
Why is there a third? The subset is of size 2, so why is the third thing out?
What, this one?
Yeah.
I looped back around. I just showed that.
Oh.
Yeah. Instead of I could expand it this way, and I went up. Yeah, another loop. Now I'm looking at subset of size 2, and now I don't care about like it looks a lot similar to the top down. I don't care about how I'm joining A and B because down below me has told me that how to do that.
I see.
Right?
This is when subset size. I see.
Yeah. Okay. So the MPDP algorithm is going to expand upon this, and it's basically the same thing. Well, at least it's sort of confusing. There's the MPDP algorithm, that sort of technique they talk about, and then of which of that there is the MPDP algorithm that's based on the DP sub one, but then collectively they're also saying that if you tack on this adaptivity piece where they use this UnionDP one or the IDP stuff, then that's also sort of part of what they're calling MPDP. But for simplicity, we're saying the MPDP is just going to be the extension of the parallel version of the DP sub. Right? So again, they're going to have that same check that Hyper or Umbra was doing about the complexity of the query to decide which algorithm they want to use. So for simple ones, they'll use DP sub to do the search exhaustively. But for larger queries, they'll use a combination of the heuristic their own heuristic technique and DP. But the difference that they're going to do here is now, instead of just picking vertices and deciding how to split based on that, they're going to do a combination of vertex and edge-based enumeration. And the goal here is that it's like, again, pre-computing what are the valid cuts you can make in the query graph to avoid having disconnection and then having additional checks later on within that for loop to see whether something is connected or not. And that's going to matter later on when they put this on the GPU, because in GPUs, you don't want branching, because you don't want your different cores or threads down within a it's a grouping or a warp, as what NVIDIA calls it. You don't want them to start going down different paths. We'll see that in a second. All right, so what's the difference between vertex enumeration and edge-based enumeration? So again, vertex is you're just exploring the search space by deciding how to pull off subgraphs of the join graph you're examining based on vertices, right? And then you then build back up the relation as you add back in the vertices. So you sort of split things up, and then you add things back going up. And then you have to again, make sure that you're not generating invalid subgraphs, because if you're trying to avoid Cartesian products. In the case of edge-based enumeration, you're going to look at the join pairs, the edges themselves, and that's how you're going to decide what you actually want to cut or not, right? So this is going to be better in terms of reducing the amount of wasted work, because you're not having to evaluate a bunch of join pairs that are you're going to throw away anyway. But now it's more difficult to parallelize, because now again you're sort of blocking the generation of these different partitions you could be exploring, the subgraphs you could be exploring, until you finish the slicing up of the joins, of the subgraph. All right, so I don't have an example of MPDP, but again, it's basically the DP something, which is how they're slicing up the edges is slightly different. But then again, they have this heuristic that kicks in when they recognize that the query becomes too complex, and they have something that looks very similar to the GU thing we talked about either last class or 2 classes ago, where they're going to look at the join graph and calculate some cost of each join, using heuristics, and then just decide which one they want to combine together. Assume that's the order you're going to apply the joins, right? So it's basically the same thing we saw before with the GU, right? You have all these edges. They don't talk about how they're calculating selectivity, intermediate results. They just say there's just a size of the result, but that's the cardinality you would get from the size of a relation and the selectivity of a predicate. So now you have a way to say, okay, here's how much data is going to come out of a particular join, and then they're going to end up picking the largest one and have that be merged together, and then that's saying that I want to apply this join first as early as possible, right? And again, they do this. They sort of split that up into the small size you have within some size k, and then they keep adding up the larger pieces until you have the full complete join graph all over again. And it's basically, in the case of GU, we saw them merging it into, combining the 2 relations together, say they're being joined. They call it a composite node, a composite vertex. But it's basically the same thing. It's telling me I know I want to join BD first. And this is going to give me the ordering that I want to apply this. Yes?
So this will work really well for Snowflake star schemas. But I was just wondering, will it work well for schemas that are not Snowflake or Starflake?
Like cliques or trees? Which like hard?
This would be terrible for cliques.
Yeah. So I mean, his statement is this would be terrible for cliques. So my understanding is that they do this. Sorry, look at it. The K. So the K matters here. So you're going to keep building this up until you have these subgraphs of size K, right? Mm-hmm. And then you take those subgraphs of size K, and then you run the MPDP algorithm on that. In the paper, yes. And this is what I'm doing. I don't know. It's a small graph, but you could do like 4 or something like that, right? So I would do this heuristic. I would end up these composite vertices now with four relation tables in them, then run MPDP on that. And so the reason why they're ordering it based on the size, so the larger ones go first, is because they want to make sure that they optimize those clusters first.
And those would naturally be very obvious and important parts to optimize if you have a snowflake or a star schema. But if you don't have that, you have cliques, then it won't.
His statement is that it doesn't make, if you have cliques, it does, sorry, your statement, because if it's a snowflake or star schema, it would be obvious which one you want to optimize first.
Yeah,
but
it would be obvious which ones to optimize first.
But in cliques, you wouldn't have that, right?
Yes.
But still, based on their algorithm, somebody's going to be have the biggest cost. Just go optimize that first.
Yeah, but then they didn't show it in the paper.
There's a lot of things they didn't show. Yes.
They say they were in the experiments, then they're conveniently not there.
Yep. There's a tech report. It wasn't in there either. Okay. And
At least it doesn't degrade the performance.
Well, for small relations, but when they do the heuristic for large joins, they give the results for snowflakes and star, but they say they ran them for cliques, but they don't show you the results.
yes. Again, I mean, so how to say this? In addition to learning a bunch of here's how to build a query optimizer, which you also should be getting from reading the papers is just one, how to read a scientific paper, but also a healthy dose of skepticism about yeah, they're saying this, it doesn't really make sense, right? And it's hard because you got to go read back the paper multiple times, what the hell are they actually talking about, right? And so, the German papers are great, but they're also very esoteric to understand. This one is missing a bunch of things, and they have a bunch of stuff that doesn't really matter. And then they cite to the longer tech report that's on the archive, but that doesn't have the things we're missing as well. So, there's not a lot of papers on query parallelization. This is one of the newest ones.
It's a great paper.
It's a good paper.
Easy to read.
Yeah, sure, yes. Okay, so again, the main thing I want to point out is so there are. It's hard to show this with a small graph, but think of a really big graph, a join graph, and you're trying to figure out again which one's going to have the largest intermediate results. And you start putting them. I don't use the term cluster, but you're putting them in a sort of composite group, and you keep going until you have a group of size k. And then once you have that, then you go run the MPDP algorithm on that cluster and figure out how to do that optimal join for that one. And then you find the next cluster and do the same thing. So again, it's you can't do the exhaustive search across the entire join graph. It would be too difficult and run forever. So instead, you're kind of zoning in on portions of it, optimizing that piece, and then hopefully that at least puts you in a good direction.
So the GU is actually choosing the smallest one, while the UnionDP approach is choosing.
Yeah. So the statement is, and he's correct. The GU, which I can bring that slide back up. The GU is choosing the smallest one.
Yeah, but that's for the linearizing part.
Yeah, that was a way to simplify the problem to generate with the join ordering. So let me bring up. Yeah, I should include the slides.
But there, the objective is slightly different.
Yeah. So again, go back and put this back in more context. So again, this is for the large queries in the German approach. And so the idea here is that the high-level goal is the same. You want to simplify the search problem because you can't do an exhaustive search. So in the case of GU, what they want to do is linearize the sort of search space so that you at least have sort of a left deep tree, and then do the more expansive search, and then look at bushy plans and other things, right? So similar to they say how big of a sort of subproblem you want to look at. They're doing K100 here. All right, so again, you have this cost, the number of tuples that are come out of a relation, and you have the selectivity. So the same thing. You do the simple math, and you end up with the cardinality. So the idea here now is they want to choose the smallest one, and you want to merge them into an update graph. And by choosing the smallest, you're basically saying that this thing doesn't really matter in terms of the entire query plan, because they're not joining that much data. This is not my big problem. So you just sort of you just combine them together so that you don't have to have in your exhaustive search, considering B and C explicitly in the search process. You're just kind of again using this as a placeholder to say, yeah, there's a join happening here, but it doesn't really matter in the grand scheme of things. So that's what GU is doing here. It's a way to hide things that you don't think actually are going to matter, right? To simplify the search process. You keep doing this recursively. So then now going back to what the UnionDP is doing, this is doing the opposite. This is trying to find the things you think are going to matter by taking one with the highest cost. And again, combining them into a bunch of nodes. And so I could use heuristics to decide how I want to join the A with BD and C with BD, but I really want to know what is the optimal best choice for me to join BD because the data set size is so huge. Is that clear? Again, it's a different approach to trying to solve, again, this really hard problem of like how do you pick the join order. And the idea of from the German paper was like, okay, simplify it through GU and then use that as the starting point, at least my initialization, so I'm not spending time just trying to find a quick upper bound. In the case of UnionDP, it's a way to sort of highlight the parts of the query plan you want to spend most of your time computing on to try to find the best join order. Okay, so I'm not a GPU expert, and so what they're saying seems reasonable. But the basic idea is that they claim that because you can rewrite, because you can get rid of those if clauses where you're checking to see whether the graph is connected when you start building up the subgraphs, if you can remove all that and just have the computation of it, we're deciding here's the enumerations I want to look at by doing it based on edges so that you don't have to generate invalid join graphs, then now you basically have this sequential code that you can run now in the GPU, and you don't worry about what is called branch divergence, where like different threads within the same warp, like a grouping of threads, are going down different code paths or paths in the same code. And then that requires the GPU, I think, my understanding is to execute them in serial order. So you kind of lose all the benefit of having a GPU with thousands and thousands of cores, because now you end up getting executed in single file. So they're going to do the same trick we talked about last class, where you represent the join graph as just an array affixed with bitmaps. That's great because, again, GPUs don't like variable length things. So if you know exactly the offset of stuff, you can jump to that very quickly. And again, as I said, they remove all the branches to remove the conditionals, get rid of the branch divergence, right? Another thing they don't talk about, but is in the paper that they cite, is you can't have the GPU threads, as you're doing this join enumeration, call back to the CPU for any additional information. Sorry, what?
Yeah, that's one of the concerns I have. Like you have to make the entire cable or the necessary data fit into the GPU memory.
Yes.
For the best performance, it should be fit into that shared memory within the SM.
Yes.
Otherwise, it will be in the HBM.
Yes.
But if it's like the data lake service like Snowflake, and you have to dynamically evaluate something that's outside that, and making such function code will be very costly.
Yes. So to repeat what he's saying, we talk about how there's this cost model thing we keep pointing to on the side, that it's going to magically tell us the selectivity of an operator or a predicate or the cardinality of an operator, right? So when we look at the algorithms before, there's always like, oh, compute this cost function within these algorithms in the paper, and that's making a call to some cost model to figure out, again, to estimate what the cost of your operator is. So where does that exist? Well, that's in the catalog, right? There's some other piece of code that's going to generate those estimates for you. So, but now if you're running your join enumeration, where it's trying to look at the cost of query plans to decide which one's better, right? It's basically looking at, like, is this thing better than this? But it's the algorithm structured in a way to sort of rip through the possible orderings you could have very quickly. If all of a sudden you got to say, okay, well, here's a valid query plan I could consider, compute the cost for it, so because you want to check to see whether that's better than the best cost you've seen so far. You can't make a call to the catalog in the GPU because Now you're going back up to the CPU and you're blocking your threads in the GPU, and you're losing all the benefits of the parallelism, right? So the paper doesn't talk about it, but the other one does, where you basically have to package up all the estimates that you're going to have for any possible joiner you're going to consider down below. That has to get sent down to the GPU with you. And that way, all the computation and analysis is localized in the GPU, and you never have to go back to the CPU until you say, here's our computational result, or give me more work to do. I didn't find anything yet, right? So GPUs are great. They're really good at doing parallel computations, which is what they're trying to do here. But you got to have everything be local on the GPU. Because as soon as you go talk to somebody else, you're blocking it, and then you're screwed. Is that clear? Okay, so this paper's got results, which is another reason I like it, right? So I'm going to cherry pick 3 graphs. So the first one is going to be, what is the search time for these different methods? The DP, CPP, CCP, that's the sort of graph-based one. It's a precursor to the hyper one. I forget what DPE is, but DP sub, DP size is system R, DP sub is the one we talked about before. But again, they have a bunch of these running on the CPU. They have a bunch of these running on the GPU as well. It's actually quite impressive, right? And so the 2 workloads they're considering are the joint order benchmark, which is based on the IMDb database. That we're going to see a lot through the newer papers we look at. This is the common workload everyone does. And then Music Brains is an online music database, and I think they generate synthetic queries for this, right? So if you look at the Music Brains ones, and again, they're scaling up the number of relations that are being joined. This seems like the GPU is the clear winner here, because everything else is falling off the cliff, whereas this one is doing okay up to like 2025. Again, it's log scale, so it's not great anyway, but it's doing quite well here, right? But then when you look at the joint on a benchmark one, it's surprising that the GPU is basically flatlined for both the DP size one and the red one here is the GPU one, right? And now you see the performance gap between what the CPU can do and what the GPU can do is not as great. And I think, if I remember correctly, it was just because of the complexity of the joint order benchmark queries. The predicates were more restrictive, and therefore there was fewer options they could consider in a parallel search. So even though GPU has all hundreds of thousands of cores, actually they're running on like a 2016 GPUs. I forget, it's like 8 gigs of RAM, but I forget how many cores they have. But still, like there isn't as much opportunities for parallel search as there was in this one over here. So that they're not getting a big of a win. And the reason why it's sort of flatline is the cost of like packaging up the request or the search for you in such a way that the GPU wants to read, sending that down to the GPU, letting the GPU crunch on it, and then come back up to you. That's why there's sort of like a fixed cost. No matter what the size of the query is, you're always paying that penalty. Yes?
So if you cut off the Music Brains graph at 18 relations, which is the highest number that the job goes to,
yes,
and they kind of look very similar.
So his point is,
so is it also the number of relations?
So his point is, like, if you ignore everything on this side after 18, it kind of looks very similar. So is the benefit you would get from from using a GPU or the parallel search, like
it's limited to high number of relations.
So again, the hyper paper didn't show crazy number of tables in a join. They mentioned there's the 5,000 one from SAP, but I forget what's the highest one they went up to in their experiments. But it was definitely, I think, a little bit higher than this. Like 30 seems like, I mean, the next slide, they go up to 100. So I think there's only 30 tables in Music Brains. So that's why they couldn't scale beyond that. And then joiner benchmark, it's just 18 tables or 17 tables.
You mean the bottom up German one? That one was like 100 relations.
Yeah. So they're gonna go to 1,000 in this one, but like, okay, so for these are real data sets synthetic workloads, synthetic queries. And so they're maxing out the number of queries that they have, the number of tables that they have in their database, and that determines how many you can do in the join. How do I say this? They didn't do the same sort of scalability experiment. I guess that's actually the next slide, but they don't show the search time, I don't think, for going up to 1,000 queries. Yeah, they show what the plan cost is, and we'll discuss that next slide.
Which is also sketchy, but it's not.
Well, okay. All right, so let's get to that. Okay, so again, so this is search time. So this is like for these given queries with a different number of relations, how well does the search algorithm scale, right? The next one they did is they measured what is the quality of the plan for these different methods relative to each other. So they didn't actually run the queries, right? They're just saying, here's what the cost model in the query optimizer thinks is the quality of this query plan. And I don't think they even try to like prove, like, run some random ordering to see whether the relative ordering is actually correct or not.
Is it because the query is just that big? Like,
No, so I mean,
you can't justify that, can you?
so that's what I'm saying. I don't think you want to do an exhaustive search of like try to run everything, prove that the ranking is correct. I mean, you could on a reasonably sized data set, you maybe could, but I think if you did a bunch of the statistical method where you randomly sample and then show that for any random sample the ordering is correct, and therefore with some kind of guarantee or confidence, I can say that the global ordering is correct. They didn't do that, right? This paper is what, 2022?
Yeah.
So that means they wrote it in 2021. So data fusion wasn't a thing back then. DuckDB was still pretty early, right? Yeah, but that would take forever, right? To run this on Postgres. Because it's a row store, right? All right, so for this one, they're throwing everything in, which is kind of nice. So GEQO, that's the genetic algorithm from Postgres. MinDP, that's the adaptive ones from the Germans. GOO, we've covered. IKKBZ is the approximation they use to generate optimal left deep trees. We saw this in the Umbra paper. And then I didn't talk about the iterative DP one. It's mentioned in the Hyper paper. It's a different formulation, right? It's a way to get it for a really large number of joins. It's a way to sort of approximate things and be easier. So they talk about how they run it, the MPDP algorithm on different sizes of K, and then they only report 15 because that's like I think the median. But they do scale up the size of K to show that different cluster sizes are going to make a difference. So this graph here, it's all going to be relative to what their best implementation can do, the UnionDP with MPDP of K equals 15. So all these numbers here are just relative to this, right? And again, it's based on the planned cost estimate from the query optimizer itself. So the query optimizer is saying, I think this query plan is going to cost 5, and this other query plan is going to cost 6. That's what they're reporting here. It's not wall clock time. You're making more phases.
We found where they talk about the results of clique graphs.
What do they say?
For a large uncommon clique join graph, we summarize the evaluation results in the interest of space.
And then they say it times out after any relations.
All right. Whereas the Germans don't, right? And then the X's here are just saying that this is when the optimizing or the algorithm failed to finish. And then for these here is when you go, these are up in like the 40 to 50 relative difference to.
The interesting thing that they say is that after, or like in general, for clique graphs, the IDP2 is much, with MPDP is much better than the UnionDP.
For what? For clique graphs.
For clique.
Got it. This is a snowflake graph. The star graph, the star schema one looks basically the same as well. But they don't have numbers on that.
Interest of space.
Yeah. It might be in the tech report. I don't remember seeing it though. Okay, so this is the one from EPFL. I want to briefly talk about another approach from IBM that predates that, since it came out in 2008. And the basic idea here is that we're going to you're going to represent the possible joint orderings you can have in a relational database. And then now when you want to figure out what kind of enumeration you want to do, now you're just doing self joins on that same table within your database to then do the enumeration. And then there's a little bit of trick they're going to do to decide how they want to allocate the task to do the exploration on the to your workers. And they're going to do this in such a way that you want to, again, to maximize the amount of work, maximize the, or minimize the amount of wasted time workers have because they don't have any work to do. So the blindly handing out, like, you do this, you do that, is not always going to work out, because it may be the case that because they're not going to figure out what are valid join orders before you actually start doing the evaluation of it, you could end up with a thread with a bunch of stuff they don't need to do and everything gets thrown away. And then they become idle. Right? So in the paper, they talk about that they're going to split things up based on what our quantifier says. Anyone remember what that was when we talked about relational calculus? Nobody. Good. Excellent. Again, beyond this class, you don't need to know this. But the quantifiers are just going to be think of like the things that are producing tuples that are being fed into other sort of blocks, right? This is from I think lecture 3 or 4 about in Starburst, right? So the quantifiers are again just things that are producing tuples, right? But they don't want to call it that. They don't want to call it like tables because it could be, again, nested queries and other things. All right, so say we have a simple query here joining A, B, C, and D, and a query graph looks like this. So in the first step, they're going to generate the set of all the planned tuples you'd have in this memo table. But again, the memo table is just going to be a table in your database, right? And then now they're going to do logical partitioning to divide up this work into groupings where the size of the subgraph, the number of quantifiers you're having in your subgraph, are all going to be the same. So what I mean by that? So the first partition P1, these are going to be where the subgraphs are size 1. P2 is all the subgraphs of size 2, 3, 4, and so forth, right? And again, it's not the ordering. The ordering doesn't matter. It's logically what's in them. And again, I'm saying logically partitioning just because you're just saying there's some other mapping to say, these rows here belong to this partition. So then now you're going to then explore each partition starting from the bottom, because we're doing bottoms up. So we have first got to figure out how we're going to do what are the subquery plans for this first partition here. And again, that's just running the DP algorithm to figure out here's the best join ordering or the best access method I want to use for this subgraph I'm examining here, right? And the reason why there could be multiple query plans is because, again, it's not just accessing tables by quantifiers. It could be like a subquery. We can ignore that. And then I go to the next one. And so now, if I want to evaluate the different combinations I could have in here, well, that's just doing a join of all the things I've generated in the first partition, P1, with itself. Because now I'm going to get up with all combinations within of subset size 2. So I do that, do the same calculation, again, yada yada, and I generate a bunch of query plans. Expand upon Q3, again, sorry, partition 3, and again, now I can only have it's a combination of partition size 1 and partition size 2, and now I just join the top one and the bottom one, so the top one and the second one together, and that gives me all possible permutations. Again, you're just doing this within the database itself. And then now I get down to this one here. And for P4, now I have two choices, right? It could be a combination of subgraphs of size 1 with a subgraph of size 3, or subgraphs of size 2 joined with itself, right? But again, this is basically like DP sub, where they're not checking as they're generating these enumerations whether the joins are actually valid. So you're just basically coming up like through these self joins. Here's all the possible tasks or join orders I could consider. And so if you do the naive thing and say, okay, well, I have 2 worker threads, so I'll give this one to the first worker thread and this one to the second worker thread. The problem is when we look down here, we know a bunch of these are actually useless and invalid because we just kind of took a Cartesian product of P2 with itself, right? So a join of AB with AB is useless because it doesn't actually contain C and D, which I need to have, right? So all of this work would get thrown away, and the only thing we're actually really end up computing is what's in this sort of task list here. So now we need to be a bit smarter on how we're going to decide which workers are going to do this enumeration, because we don't want to assign this one thread. It throws everything away, and then it's idle. So this paper really is really focused on how do you do that allocation of the work I have to do to the workers that are available to me, and doing it in such a way where you're mindful of what the join graph is actually looks like, to make sure that you are evenly distributing the work amongst the different threads. In the case of the MPDP paper for the GPUs, they're kind of throwing everything in there, and then you have so many cores. Who cares, right? 2008, there was basically like 4-core, 6-core machines. Not the sort of behemoths we have now, but still. All right, so the first thing to do, the easiest thing to do is just like do what I said at the beginning, is you just take all the possible planned joins I have, divide it by the number of workers I have, and just hand them all off. It's the easiest thing to do, but again, it's going to be, you have imbalance in the workload because one worker could have a bunch of stuff that throws away and there's nothing to do. So instead, what you do what they call a stratified allocation, where you want to divide the work I have to do into sort of multiple subsets, and then hand them out in an intelligent way to kind of try to evenly distribute the work I want to give out to my workers. So the three ways to do this is, again, if you just think about the join enumeration as a self join, like a nested loop join, then now I can think about it in terms of like what's the outer table and the inner table, the outer loop and the inner loop, right? So in this case here, I have my outer loop would be this line here for I in 1 to this floor the size of I2. Right? That's an outer loop that's going to be grabbing sort of one half of a join graph, and then now you have an inner loop that's going to say, okay, look at all the possible combinations I could have, or the different join orders I could have for the rest of the subgraph. The question is, how do you want to assign that evaluation out? So equidepth says you just take, I know what my outer loop looks like, and divide it into ranges amongst the threads that I have. So like within one iteration of this outer loop here, one thread would take all of that, right? All of the things you want to do in the inner loop. Another one would be every time you iterate through the outer loop, you just hand that work off to one worker in a round robin fashion. And again, then they take all the work that's within the inner loop. The alternative is that you do the round robin within the inner loop itself, right? So distributing the outer one, it actually turns out to be the best, because you end up, it works really well for star schemas and other queries that have skewed joins, because you're kind of handing out the easy problems evenly amongst everyone else, amongst all the different workers, right? This one works well too, but it's a little more complicated to figure out in the calculation. But this can handle, again, the skewed workloads, star schemas, and snowflake schemas as well, right? It's really great when you have a central table that's really large, because now you don't have one thread trying to figure out all the joins for that really large fact table, right? Because it's iterating all through the dimension tables on the inner loop here, the work is spread across multiple workers. Okay, so let's finish up. So hopefully the main takeaway from this is that the idea of or how to divide up the join search, or the join ordering search, is complicated to parallelize, because again, there's so many things you got to worry about. Not just like how do you divide work up so that everyone is all the workers are active and have stuff to do, but also how can you do do the enumeration ahead of time so that you don't generate a bunch of work that's actually useless. So that part is super tricky. In terms of whether or not it makes sense to run the optimizer on a GPU, I would say the way NVIDIA keeps jacking up the prices and the scarcity of discrete GPUs, like again, they were running on a GTX 1080, which was high end, but high end 6 years ago. Nobody would want to say like, I'm going to run my database system, but I also have to have like a $10,000 GPU on it, right? Just to do join optimization, right? I don't think that's feasible and practical. But there are CPUs now that come with what they call, these AMD calls them APUs. They're basically integrated graphics chips, right? And so like you can now get like Ryzen, this is from 2 years ago, but you can get Ryzen CPUs that'll have like some kind of radon thing in there. Is it going to be super powerful, like a 5090? No. But is it going to be better? It's going to be a lot of cores? Yeah. And that might be something to be interesting now when you're, since it looks like there's sort of limits on number of cores they can cram into a general purpose CPU, that seems to be not increasing as much as it used to. Like that's another opportunity where like this is something the database could take advantage of. If there's a cheap GPU right there, it's not cache coherent, but that's not a problem, right? For joint search, like that might be something the database could take advantage of to do the MPDP algorithm we talked about today. But I don't think Amazon. You can't get something easy too. You can't get an AMD processor with an APU. But
the paper also shows that this kind of the age of GPU only starts to show after specific like number of relations, and at that stage we're not sure whether this low-end GPU will still have some performance advantages.
All right. So his statement is the paper shows that the GPU really only makes sense when you get to a large number of relations, right? And it's not clear whether you would actually, for those large number of relations, you have to have a discrete GPU, or would an integrated one be sufficient? It depends. I think one is, again, if every CPU is coming with this now, and it's just there, you could take advantage of it. The other thing you could also think about is like, well, if I already have to bundle up the join enumeration to put it down to the GPU so it doesn't talk to my CPU, there's no reason that has to then run on the same box that I'm at. So if I'm like a snowflake or running database as a service, as a business, I could have a bunch of GPU machines sitting on the side that I could then send these discrete requests to do join enumeration on that. And then that way it's a shared resource across multiple things. And then it amortizes the cost across multiple, multiple customers. Yes, that could be part of it, but I think that for better or worse, from a business perspective, it'd be very hard to justify, hey, we got a bunch of buy, H100s so we can do join enumeration versus like trading an LLM to, do some chatbot thing, right? Do I think join enumeration is a more important thing? Yes, but like that's just sort of not it's not the hot thing. It's not going to get people, oh man, I'm going to buy, I'm not going to give NVIDIA $100,000 to make my join enumeration look a little bit faster. So again, these things might be a cheap way to achieve some of those benefits. But to your point, yes, it's not clear whether the integrated ones can still handle it. You'd have to look at what the hardware specs for what this is now versus what their 1080 was 6 years ago. Okay? All right, so that's it for today. We'll pick up again on Monday next week and start doing again parallel search now for the top-down stuff. Okay? And then we'll also present some of the potential topics for project 2.
Little glazed brown. Matter of fact, hold the fuck. This is that wood grain type of shit. Shout out to Blockhouse, my dogs. Get one, Big Al, Mike Stroke, Drumley, all Dynamites. I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thug from the gun. Shit, some niggas claiming never rapping is sudden. Don't push the button, yes you motherfuckers in front and you don't want nothing. If it did, it'll big start something.